So next we're going to look at the characteristics of the normal curve. Now this is the distribution that we use most often in statistics to talk about how to fit a curve to most histograms of our output data. And so it's the normal distribution, the bell-shaped curve, Gaussian distribution, and we use it because it represents naturally distributed things like height and weight and shoe size. So if I were to go sample a room full of folks, as long as I don't have some basketball players, I'm going to get a nice distribution of heights or weights or shoe sizes or inseams. Those follow a nice bell-shaped curve. Manufacturing processes, so we sometimes call it white noise. The drift in the bearings, the motor speed, setup errors. Over time, when I create my histogram of my output, it's going to follow this normal curve. It's also the assumed distribution for measurement system error. So when we talk about adding variances, we can always add variances from normal distributions. And then we're also going to use this as the distribution for errors when we build models. And so when we do regression and we do designed experiments, we're going to make the assumption, and we're going to check it, we're going to make the assumption that the leftovers, all of the error, follows this normal distribution. So what's the big deal about this normal curve? Well, we know a lot about the normal curve in terms of its characteristics. We can even start at the simple thing. The mean, the median, and the mode are all in the same location, so that's kind of nice. So I know if I compute the average, well, that's where the highest point in the distribution is going to be, and that's also where the median is for a normal distribution. I know the area under the curve from minus infinity to plus infinity is equal to 1, and by any place on the curve, I can tell you how much area there is either to the left or the right, or I can even take chunks out of the distribution in the middle. For example, plus or minus 1. Standard deviation is 68% of the data. So I know a lot about the curve, and I can use these things to my advantage when I'm calculating things like defect rates, and we're going to use this again when we start to talk about hypothesis testing. If I know I have two normal curves, I can tell you whether or not they overlap or don't overlap based on how much area there is out here in the curve. Other advantages of having normally distributed data. I used to show a picture of this really large spreadsheet that had lots of numbers in it. And I would go to the engineers and I'd say, what are you going to do with all this information? And they would kind of look at me funny, and I'd say, well, if it's normally distributed, I can calculate the mean and I can calculate the standard deviation, and then I can throw the whole data set away, because those two parameters, I can recreate that information over and over and over again. So I can redraw my curve with just two numbers, the mean and the standard deviation. We already know the shape, we already know the area under the curve, and as we said before, the hypothesis tests for normal data are very well defined, and they've been around for decades and decades. So we have some advantages when we have continuous data, and that continuous data forms and follows a normal curve. So now that we've hyped up a normal curve so much, well, what if it's not? And the next few slides are going to show us, well, it might have started as a normal curve, but something happened that caused it not to be. And if you can start to read into the output data, you might be able to get some insights into what caused it to be non-normal. It wants to be normal, but it's not because, and we're going to look at some of those reasons.